Discover how to design powerful DFAs that can recognize complex binary patterns, enabling you to solve real-world pattern matching problems effortlessly. Learn to visualize and explain the inner workings of these automata without getting lost in abstract mathematical notations. At the end of this lesson, you have designed and drawn a complete DFA diagram that recognizes binary strings divisible by 3, including all states, transitions, and the acceptance path for the input 1101. Additionally, you have written a brief explanation of how the extended transition function D processes this input string through the automaton. Jake was working on a data migration project for a logistics company. They had hundreds of exported files in a weird custom tracking format. There was no official parser for it, no open standard, no documentation, and the fields could appear in any order, sometimes with extra noise. Initially, Jake tried using Regex and split functions. It worked, until it didn't. Edge cases popped up, missing fields, invalid order, repeated keys. After spending an hour debugging nested if-else statements, he paused. Instead, he drew a DFA on paper. He implemented it using a simple state machine loop. The result? A parser that handled every case, even malformed lines, and flagged bad records gracefully. They used the same DFA design later to validate incoming webhooks with variable formats. What is a DFA? The full term is Deterministic Finite Automaton, or DFA for short. Let's break that down. Deterministic means there's no guessing. The machine always knows what to do next. Finite means it has a limited number of steps or memory. It can't remember everything. Automaton means it's like a machine or a robot that follows rules. So, a DFA is a theoretical machine that reads a string, one symbol at a time, and decides if the string follows the rules of a specific language. This is part of automata theory, a key area in formal languages and computation. Components of a DFA. Let's now learn the formal definition. A DFA is a 5-tuple. Yes, that's a fancy math word for a list of 5 things. DFA equal Q, S, D, Q, 0, F. Let's decode each of those. Q, a finite set of states. These are like the moods of the machine. It can only be in one state at a time. S, sigma, the alphabet. The set of symbols the machine is allowed to read, like just 0, 1 in binary. D, the transition function. This tells us, if you're in a state Q and you see symbol A, where do you go next? In symbols, the QA, next state Q0, the start state, where the machine begins before reading anything. F, the set of accepting or final states. If the machine ends in one of these after reading the input, the string is accepted. Let's repeat this once more, slower. A DFA has a set of states, Q, an input alphabet, S, a transition function, D, a start state, Q, a set of accepting states, F. You'll see this definition in every formal CS textbook, and now it won't look scary. Example DFA, language of strings that end in 0, 1. Let's design a DFA that accepts binary strings that end with 0, 1. We define S equals 0, 1, binary alphabet. Q equals Q0, Q1, Q2, Q0 equals Q0, start state, F equals Q2, only Q2 is accepting. Now define DU, state input. 0 input 1 Q0 Q1 Q0 Q1 Q1 Q2 Q2 Q1 Q0. Explain. Q0 equal start Q1 equal just saw 0 Q2 equal saw 0 followed by 1 accept. So DFA accepts string if it ends in 0 1. Any other ending rejected. We have now used all the 5 DFA components formally. A note on extended transition function. The transition function D takes one symbol at a time. But what if we want to see what happens to a whole string? That's where we use D, called delta hat, the extended transition function. The QW means if we start in state Q and feed the string W, where do we end up? We define D recursively. The QE equals Q on empty string, stay in same state. The QAW equals the QAW. This is used to define when a DFA accepts a string. A string W is accepted by DFA M if the Q0 W F. That is, if we end up in an accepting state after reading all of W. Example DFA, binary strings divisible by 3. Let's now define a slightly more advanced DFA. L equals DAO 0, 1 will represents a binary number divisible by 3. We define Q equal Q0, Q1, Q2, Q0 equal start state, remainder 0, F equal QOL SEL 0 1 transition function the state 0 1 Q0 Q0 Q1 Q1 Q2 QO Q2 Q1 Q2. This works because appending a 0 equals multiply by 2, appending a 1 equals multiply by 2 plus 1. This DFA uses modular arithmetic mod 3 to keep track of remainders. Again, we are using the formal structure of a DFA here: Q, S, D, Q, O, F. Key terms to remember: DFA, Deterministic Finite Automaton, S alphabet, allowed input symbols. Q, set of states. Q0, start state F, set of accepting states, the QA. Transition function, next state from Q on symbol A, the QW. Extended transition function, final state after full string W. DFA design strategy. When you design a DFA, define the language clearly. What pattern do you want to accept? List the states you'll need. Each state equals a memory condition. Decide transitions. What symbol causes what change? Mark the start and accepting states. Use D if needed to analyze longer strings. Test with examples. Try strings in and out of the language summary with jargon. Let's tie it all together. A DFA is a 5-tuple Q, S, D, Q0, F. It processes strings deterministically. It can only recognize regular languages. The helps us trace strings end to end. DFAs are used in lexical analysis, pattern matching, protocol design, and more. Learning DFA builds the foundation for pushdown automata, PDA, and Turing machines. What's next? If you now feel comfortable with the terms, try converting a regular expression to a DFA. Explore NFA versus DFA, non-deterministic versus deterministic. Learn about DFA minimization, merging equivalent states. Perhaps you're thinking that designing DFAs is too abstract and won't have practical applications in your work. Remember, DFAs are fundamental to many real-world systems, from compilers to network protocols, and understanding them will enhance your problem-solving skills across various domains. You might be concerned that creating a DFA for binary strings divisible by 3 seems too specific to be useful. However, this exercise teaches you how to model mathematical concepts using state machines, a skill applicable to numerous computational problems. It's possible you're worried about the complexity of the extended transition function DFAs. Keep in mind that while it may seem daunting at first, mastering this concept will give you a powerful tool for analyzing and describing the behavior of any DFA, regardless of its complexity. To achieve the result we've set for this lesson, please do the following. Step 1. Design a DFA that recognizes binary strings divisible by 3. Draw the complete diagram on paper or using a digital drawing tool, including all states, transitions, and clearly marking the initial and accepting states. Step 2. Trace the acceptance path for the input 1101 on your DFA diagram. Use a different color or dotted line to highlight this path. Step 3. Write a brief explanation, 2 to 3 sentences, of how the extended transition function D processes the input 1101 through your automaton. Focus on describing the state changes at each step. You'll know you've completed the task successfully when you have a fully labeled DFA diagram with the traced path for 1101 and a clear written explanation of the extended transition function's operation. Please download and fill out the worksheet to document your DFA design and explanation.